accepting this invitation and making the effort to give a presentation today in spite of having a different time zone.
Okay, do you hear me?
Yes.
Perfect. So thank you, Manuel, for the introduction, and thank you for the invitation to getting me on board of this wonderful workshop. And the topic of my talk is about low dimensional magnetism, and especially a new type of magnetic universality, which is easy plane magnet or XY type magnet. And I will describe a specific case, which is monolayer chromium chloride as an experiment. And this is a relatively recent work, which has been submitted, and you can find more details in this archive reference. So I have to comment also here that it's a beautiful example of how synchrotron radiation can help to investigate monolayer magnetic samples and reveal the intrinsic properties of them. So that's also actually good for the vein of this workshop. So let me start first acknowledging the people that are participating in the project. And first of all, our director of the Max Planck Institute in Halle, where I work, Stuart Parkin, for the excellent support and mentorship. And then the experimentalists, where I closely collaborate with, Jingron Ji for sample preparation of the monolayer chromium chloride, Kai Chang and Paolo Sessi for excellent support in STM measurements, which we use as additional characterization, and also Vanindra Pandeya for also helping in the synchrotron beam times. And it's worth to mention that this magnetic characterization of the samples has been done by X-ray magnetic circular dichroism, and it has verified in two independent beam lines, one in ALBA Barcelona and also in BESI in Berlin. And that's why I want to also acknowledge the excellent collaboration and support from Pierluigi and Manuel from Boreas in ALBA, and also from Florin Rado and his team in the BECMAC beamline in BESI. So let me start outlining the talk. So in the introduction, of course, since it deals from low dimensional magnetism, I will give an introduction of this XY type magnets in a general frameworks, also comparing with other types of Ising and Heisenberg magnets. And I will directly for a monolayer grown by molecular beam epitaxy, and the approaches that we use also to measure the properties without exposing the sample to air, which is also very important. And then I will wrap up with a summary and outlook of further experiments that can be done starting from these results. So just to give you a brief recall of the state of the art, maybe you already know that a few years ago, there has been a rise of interest in these 2D magnetic materials, and especially these three examples were the first ones that have been, let's say, rediscovered, because these are van der Waals systems. So they have been proven to be, to have long range magnetic order in the monolayer limit. And the idea here is that they need an anisotropy to break the restrictions that are given for the Mermin-Magnet theorem for the samples to be magnetic at all in the 2D limit. So of course there are van der Waals systems, and you have people have started from a few layer samples, bilayer, trilayer, but here I will just focus on the true two-dimensional limit. So I will just give examples of real monolayer samples that have been studied magnetically, and these three candidates or these three materials have been measured to have a sizable out-of-plane magnetic anisotropy. And most interestingly, there has been a lack of van der Waals systems with an in-plane magnetic anisotropy. That's actually just a curiosity from these recent developments. So let me just describe a little bit more about anisotropies and what happens for 2D materials in the magnetism in the 2D limit. So there are three main type of magnetic systems, and you can classify them one criteria is, of course, the anisotropy, magnetic anisotropy. And as you see here, there are the Ising type, XY type, and Heisenberg type. And as I said, the anisotropy also gives the spin dimensionality of the system, which is you have here increasing from 1 to 2 to 3. And that gives you basically that the magnetic material would like, or the magnetic moments would like to point either in one direction, as here the Ising type magnets. The spins are confined into a plane, so they can point in any direction in the plane. And the fully isotropic case is the Heisenberg type magnets, which where the spin can point in any direction in space. And especially here, as I was saying, is this the assessment of the anisotropies as important criteria that will be also important for later in the talk. So a second way to distinguish these three magnetic universality classes is to look at the phase transition. That's another way how to distinguish them experimentally, because each type of magnets will have a particular critical exponents at the phase transition. What is actually that? You have, for example, this type of order parameters such as magnetization or susceptibility that will decay with a power law close to the, in this case, magnetic phase transition, and it will be characterized by an exponent. In this case, beta and gamma, they are particular for these two quantities. And depending on what kind of exponent you get, you can easily also classify in which regime you are in this magnetic type materials. So in the case of Heisenberg type, of course, since you have a fully isotropic case, you don't expect to the magnetic order in the true monolayer limit. That will also be important. But we have to acknowledge that this has been already studied. So the community working on van der Waals magnets, of course, it has been a recent interest, but there have been also people working just in surface science, growing classical magnetic monolayers such as cobalt, iron on crystalline surfaces. And here there have been already a lot of studies of Ising systems, for example, in monolayers or few layer these magnetic materials with both perpendicular magnetic anisotropy and also with in-plane magnetic anisotropy. That means that we have a strong uniaxial, can then be out of plane or in plane. For the case of XY magnets or easy plane magnets, the examples were more elusive. So we have here some few examples of few layer samples that with different crystal symmetries that have been claimed to have this easy plane symmetry. And of course, there have been also a little bit of Heisenberg type magnets that have been studied before for this in this surface science magnetic community. So if we look at the current state of the art of van der Waals systems, of course, in the introduction, that was the initial, a few years ago, the initial rediscovery of these two-dimensional magnets. And there have been also some other studies regarding Heisenberg magnets, such as CGT or vanadium 5, selenium 8. Interestingly here, they lose magnetic order, or they have weak anisotropy when they have in a few layer regime. But when you go to the true two-dimensional limit, they lose magnetic anisotropy. That's why they have been classified as a Heisenberg or anisotropic Heisenberg system, with a weak anisotropy. But interestingly, in the world of van der Waals magnets, there has been no report still for easy plane magnets. Actually, that's one question that has been already pointed out much longer before, because it's very difficult to attain this kind of 2DXY behavior. Why? Because usually any type of perturbation of your magnetic system will tend to point or to direct the anisotropy in the uniaxial case. For example, again, with these two communities working on low dimensional magnetism, the people working monolayers on surfaces, if they have a strong crystalline field from the substrate, it will influence the magnetic layer on top and will always drive the system to a uniaxial magnetic anisotropy. And also this symmetry of the underlying crystal will also influence the type of yeah, the type and strength of anisotropy also depending of the symmetry, if there's twofold, fourfold, or sixfold. So there are some issues that need to be overcome to attain a really can freely rotate inside a plane, because that means you don't need any perturbations, at least in the plane. And the community of chemists working in layer bulk materials, so bulk crystals with very large thicknesses, they, of course, we have a weak interlayer exchange, but you cannot never get fully rid of it. So the only way of the crystal to the monolayer limit. And furthermore, there are also theoretical and experimental studies that usually when you drive crystalline fields on these monolayer samples, you will have between icing and XY, depending also on the type of symmetry that you have. So usually in the theory, they calculate an easy plane system with kind of perturbation, fourfold crystalline field perturbation. And here in this case, you have a competition with these two. And interestingly, of all these symmetries, the sixfold symmetry, which is the hexagonal symmetry, will be the less perturbative for an ideal XY model. So that's also interesting to know, because what we actually want is to see if we can get some ideal 2D XY system. So just to summarize this introduction and how we get to this ideal 2D XY systems, what we need here is a minimal substrate interaction. That means we have to get rid of all the crystalline fields dribbled through a Van der Waals gap. We should not have interlayer exchange, so we should make sure that our system is a true monolayer sample. And in terms of symmetry, we should have a preferably sixfold symmetry in the plane. So that's why we came to this system, which is an hexagonal system, chromium trichloride, which grown on graphene, which is also a Van der Waals substrate. So that's what our approach to get to this 2D XY regime. So just for the ones that doesn't know the material itself, so chromium trichloride in the bulk is an antiferromagnet, and you have alternating layers. It's a collinear ferromagnet, so you have alternating layers of spins pointing in alternating directions. So the intralayer coupling is governed by super exchange via chromium, chlorine chromium. And also interesting is that in the bulk, the anisotropy is weak in the plane. You have still interlayer exchange, but the anisotropy in the plane is relatively weak. And you usually have very small critical fields to somehow perturb or destroy this antiferromagnetic phase. So here you see the phase diagram, and here you have the reference for the bulk systems. But our questions were, if we go to the monolayer limit, because we will just, let's say, get rid of the interlayer exchange, if this one monolayer chromium chloride will retain this ferromagnetic-like fashion in the first layer, and it will not order magnetic at all, because we are now in the two-dimensional regime. Well, another important information is that the exfoliation community could not achieve so far the isolation of a stable chromium trichloride monolayer. So that's why we rely on a different approach to grow the samples, which is bottom-up growth in ultra-high vacuum, which is molecular beam epitaxy. And that will give us also the desired compatibility with ultra-high vacuum synchrotron techniques. So this is the experimental setup. When we grow the sample, we have here a kind of a UHV cluster with several MBEs and also characterization, where we grow and characterize the samples previously to the magnetic characterization of the synchrotron. So we have here, for example, XPS or STM to check morphology or chemical properties of the sample. So just regarding the growth of the samples, we used silicon carbide, and we prepare from silicon carbide graphene in vacuum. So we graphitize the surface and we end up with bilayer graphene. We check carefully via STM the coverage and the properties of the graphene before depositing the chromium chloride. And when we grow the chromium chloride, we have to make sure that it's a monolayer, that is not a thicker sample. And we do it via in situ techniques, diffraction techniques such as READ. And with this diffraction technique, you can easily see that the pattern of the substrate changes depending on the crystalline symmetry of your grown monolayer, and we stop the growth when the pattern of the substrate varies in this case. Interestingly, the growth has a peculiarity, and it is that it's not fully single crystalline oriented in the plane, but it has some twisting of the domains, and it has some preferential directions because you have here really streaky patterns that corresponds to one to the gamma m and gamma k direction of the hexagon. So we have two preferential. So the twist is around 30 degrees preferentially. So we will see later in the STM characterization that when you this is again an STM image of the whole sample is chromium trichloride grown on graphene. So what you see here, these atomic terraces come from the silicon carbide. So you can imagine you have atomically flat terraces of silicon carbide, and then you have like a carpet, the graphene and the chromium trichloride monolayer on top. How you can assess that you have the material on top of course, on top of READ, we have done STM measurements, and we see a moire pattern that is characteristic of a superposition of chromium chloride and graphene. The grain size of the in this sample, in this thin film, is around 200 nanometers. And if you have STM in different places, you can see also different moire patterns, which also suggests you that you don't have a homogeneous single crystalline interaction in the plane. That will be interesting later for the discussion of the results. So again, before doing the magnetic measurements via X-ray magnetic circular dichroism, we also perform some preliminary characterization to make sure that the transfer of our sample has been successful. So we transfer the sample via an UHV suitcase with a base pressure of 1×10⁻11, so it's pretty good devices. And the Stern test was to transfer this from our MBE to our low temperature STM. And we did a spectroscopy on the chromium trichloride monolayer. We could here measure a band gap of 1.6 eV. And with no defect states and no perturbations. So that means that the chromium trichloride is pretty pristine in our monolayer sample. So we don't have any defect states, and we don't have any also electronic perturbation from the substrate. That's also important to see. In addition, we perform also some chemical characterization. This is already done at the synchrotron, preliminary measurements, where you see that there's no traces of oxidation, and instead you have a pretty sharp chromium edge that is actually also gives you the quality of the sample. So saying that, we did just a brief, many of you already know this technique, but just for the ones that doesn't know. So we did XMCD, X-ray magnetic circular dichroism, and this is a technique, local technique that probes the magnetic moment of the sample via uses different absorption cross section for circularly polarly slide in left and right, and in that case you can map the imbalance of these spin bands, and that's for a 3D transition of iron cobalt, for example. And interestingly, this XMCD signal that you will get here when you measure the electron yield, for example, in these bands, will be proportional to the magnetic moment. And the advantages compared to other techniques like MOOC, which is also widely used for this van der Waals magnet, is that you can study element-specific magnetism. So you can go directly to the chromium or the chlorine edge and see how the magnetic moment evolves. So that was also interesting for us to get to know that. So just we got to the experimental results of XMCD. So this is at low temperatures at high fields. We have a very large XMCD signal, around 100%. That means that we have a large magnetic moment at low fields and at high fields and low temperatures, but that doesn't tell you any, still not much, because many systems can be magnetized in that conditions. So again, we did also some XMCD measurement on the chlorine edge, and we see also that we have an XMCD signal, which is also sizable. And that means that chlorine also participates in somehow in the magnetic coupling of in the systems. But what we would like to see is that if it's ordered ferromagnetically, this sample, so we did this XMCD as a functional field, the so-called hysteresis loops. And what we found out here is that we could due to the large XMCD signal, we could resolve very nicely the hysteresis loop at different temperatures. And we have seen, that between 12 and 15 Kelvin, the material undergoes a phase transition, a magnetic phase transition. In that case, this is a very typical of a ferromagnet, and you have the nearly vanishing of remanence and coercive field in these temperatures. So again, important ingredient for that is the anisotropy. You have to have some kind of anisotropy to sustain a finite Curie temperature. And in the end, what we did is also to investigate the anisotropy by XMCD. And we interestingly found that the anisotropy was measurable, and it was relatively large, I would say. The anisotropy fields were 0.5 or 0.6 Tesla when you compare the normal incidence versus Gracie incidence, which is related to out-of-plane and in-plane magnetization. And if you look here from the theory, the anisotropy for a really ideal, relaxed chromium trichloride was so weak that some theories were predicting that the EC axis were out of plane, not in plane. So that was for us also two important informations. One, we definitely assessed that the EC axis is in the plane of the system, and secondly, that the anisotropy is relatively large. So just to follow up, the anisotropy energy can be composed of the three main components from single ion anisotropy, dipolar, and magnetic exchange. I will just briefly give you some reference in a paper that is a PRL, very recent, that on top of the, let's say, more classical contribution with this single ion anisotropy and dipolar term, they also consider a magnetic exchange term. So for more details, you can read this paper. And the important parameters for us to investigate, to quantify a bit more the anisotropy was the orbital moment, anisotropy, the spin, orbital coupling strength, a trigonal distortion that comes also into play, and also the degree of covalency of the band gap. So especially this, we could extract from STS, from our STS measurements. And this is a constant. And these other two, we also aim to try to quantify these two quantities. So if you know a bit more about XMCD, you can perform some rules. And you can, in the in-plane of out-of-plane direction of the magnetic field, you can determine the spin and the orbital moment. So the most important result here is that we have a spin moment close to 3, which is expected for a chromium tri plus in this octahedral configuration. And the most important thing is that the orbital moment was not quenched, which is also expected for this kind of systems. So it was finite, and most interestingly was different for the in-plane and out-of-plane direction. So here we can extract a term that enters the single ion anisotropy, and that's presumably what causes for us the magnetic anisotropy. And a second thing that we try to prove is the distortion, because we are not dealing with a perfect chromium trichloride. So we grow this by a MBE, but still they are grain boundaries, and there are other cases where you can have a distortion. And indeed, what we did is, it's not a very direct measurement, so it's not X-ray. You don't resolve the lattice constant, but you try to catch the bond plane and the bonding angle of this octahedra, and then you do angular dependence X-ray absorption measurements, and you can here clearly see when you have the pre-peak at the pre-edge, which is actually the pre-edge is usually the states that hybridize here the bonds. And you see here that that you have a distortion compared to the calculated bond plane angle that is given by theory. So we have here also a large trigonal distortion that could be also helping us to have the anisotropy in this chromium trichloride monolayer. So just to wrap up here, the counts, let's say the maths, if you sum up all the contributions, you get with around 1 Tesla, which is a bit higher than what we get in this in experimentally. But indeed, the order of magnitude is just, it can't be justified, let's say, that by a single ion anisotropy and trigonal distortion, you can have an anisotropy in this chromium trichloride and thus a finite Curie temperature, which is actually also close to the bulk. So the bulk is 17 Kelvin in chromium chloride, and in our case, we will have now a closer look to the phase transition. So in the last few minutes, I will just also give you the second criteria for distinguishing, because what I want to tell you here is that we have now the intrinsic 2dxy magnetism, and we have here plotted the magnetization, that is the XMCD signal at zero field. Those are the remanent magnetization, and we have a look close to the phase transition, and we can fit the critical exponents, as I told in the introduction, that are particular for Ising or XY systems, and we see that in the XY case, the data fits very well to our close to the phase, between 12 and 13 Kelvin. So that gives us more confidence that we already anticipated that was not an Ising system, but here we have unambiguously proved that with XMCD, we have this XY type magnet with a TC of around 13 Kelvin. So a second criteria or a second cross-check we did is besides this critical exponent of the magnetization, we took also an additional order parameter with the susceptibility, and you can drive here this kind of arrow plots, which gives you at the same time susceptibility and magnetization critical exponents. And what the data here also fits very nicely with the critical exponent predicted for the 2dxy model. So that is actually the main message of my talk, MBE preparation of this monolayer and investigation by XMCD, that we have a new type of magnetic class that was not present before in case of van der Waals magnets. And the implications for that is that when you have these 2dxy magnets in monolayer chromium trichloride, first of all, it's interesting for heterostructures because it's the first monolayer magnet that is with in-plane magnetization. More fundamentally, you can have a look to the Berezinski-Koselin-Thules transition. This is also has to do with 2dxy systems, and this will also very nice to investigate the if there is some kind of topological vortex order, like in superconductivity. It's the analog. It's actually where has been this transition has been more. That's actually fully unknown if this transition indeed happens, and they give you also these topological spin textures that can be also close to the phase transition. Maybe we can observe in this system, because these are like this vortex states. In this case, it's that in-plane analog of a Skyrmel, it's a meron, and that will be also interesting in conjunction with this BKT physics to understand or to see via any technique, experimental technique, we can find this kind of merons close to the phase transition in this monolayer chromium chloride. So finally, the key factors to achieve this magnetism was the quasi-freestanding nature of the chromium trichloride, which have been grown very carefully on graphene, and the weak anisotropy in the plane, which is given by the hexagonal system symmetry with the, and with this, I thank you for your attention.
So, thank you, Amilcar, for such a nice talk. And now is open time for questions. We have 5 minutes for questions. So there one question from Joaquin Fernandez Rosier. Is there charge transfer between graphene and chromium chloride?
I would say that if there is any, it's very little, because we have done these STS measurements where you can see pretty clear band gap. We don't have any peak or any mid gap states where you can say, okay, we have some kind of hybridization or charge transfer from the substrate. So we believe that this is decoupled, electronically decoupled from the graphene substrate. So at least from that, we cannot tell that we have chance transfer. There has been no theoretical, as far as I know, no theory regarding that. If any conditions will induce the charge transfer, what we know is that from the MBE growth, the van der Waals gap is really preserved, because from exfoliation techniques, sometimes you can apply more pressure or less pressure, and you can have some different, probably van der Waals gap can be more tuned, more probably a little different. But in MBE growth, you have a peculiar growth mode that allows you just to distinguish and to have this decoupling. So that's my question, my answer to your question.
Thank you. So, is there any other question? Let's see.
I have a question for you, Amilcar. From the point of view of
yes,
of experiments, what are the main limitations or the directions where you can think that we can improve at ALBA the instrumentation in order to have better capabilities for investigating materials such as this chromium chloride, and also in particular in the case of SMCD, but in general?
In general. So I will start with XMCD. Another way to what have improved here, we have proved this easy plane magnetism via critical exponents, basically, which is this this scaling, which is also nice. But you can also prove the anisotropy when you rotate the sample in the plane and apply in certain directions the magnetic field, and you can measure the XMCD. You can prove directly the anisotropy in that way. So that would be a technical thing to implement, like let's say a rotatable sample holder, which can sustain low temperatures, and also just by challenging, I know, that would be one direction just to prove the anisotropy in the plane of these materials. Now, for that case, is particularly important. So, and in general, I would say this is very interesting, the observation of these topological spin textures. So some imaging technique textures. I know there are people working on skyrmion imaging with some synchrotron techniques. And that's actually also very interesting and important, especially for samples grown by MBE, because you have really no perturbation whatsoever, and that's very would be very nice to see in a freshly made sample if you have this kind of topological spin textures. And I at least for XMCD, I can tell that MBE growth plus UHV synchrotron gives you excellent signals, and yeah, the resolution to have such kind of studies. And yeah, imaging techniques, magnetic imaging techniques in the synchrotron would be also complementary to that, a good asset.
Thank you.
And I have a question myself regarding the question of Rosier. Have you done or have you planned to do some photoemission experiments to assess this charge transfer, for example?
Yes, we have tried to do angle resolved photoemission of chromium chloride. The problem is that we see we can't map the graphene side, but due to the flat bands and the insulating character of monolayer chromium chloride, we cannot have very good resolution of the band gaps. So basically, we mostly see graphene, the dichalcogenide and how it is placed, but we cannot see much about the change in the bands, for example, for different growth conditions and so of the chromium trichloride. But maybe let me comment in another thing that we are doing. We're trying to not only use graphene substrate, but more rigid substrates also to grow the chromium chloride. For example, only silicon carbide. Only silicon carbide will have a stronger, we believe that we'll have a stronger connection to the substrate, and we can have, let's say, more yeah, more coupling. We can tune the coupling in that way, going from fully van der Waals substrate to more rigid crystalline substrate. And that's I think I forgot to mention, but now that we are here, the idea would be to tune between 2DXY or Heisenberg Ising by tuning the crystalline fields, for instance, or the coupling to the substrate. So your questions are also very relevant, not only for the electronic properties, but that are also connected, but also directly connected with the magnetism. Yeah, the substrate issue, it's very, very critical.
There is one question from Debora. Debora, you can.
Yes, thank you. So no, it was concerning your what you said, your problem with the ARPES measurement, because it's possible that with MBA you have a small domain on graphene that with different orientation, and this is the reason why you see a sort, when you try with ARPES, you see a mix of this orientation of this different domain of your chromium chloride. Is possible, or you know the size of your domain and the orientation respectively?
Yeah, that's of course. Yes, that's another thing that will, let's say, broaden the bands. We don't have a fully polycrystalline samples. We have some kind of preferentially oriented grains inside the plane. But indeed, that could be also, we haven't studied it in detail. We could not get some, we have so far not tried with high brilliance sources, with synchrotron sources. We have just done it with a momentum microscope that we have in-house. So that's, I think it's good to have, of course, we can maybe discuss later the possibilities also in ALBA to conduct this kind of measurements, yeah, and to optimize the samples, let's say, for a good measurement. Because yeah, we are more interested in magnetism, of course, and since we don't see any correlation with the electronic properties, we were not focusing, but in the end, it will be also interesting if there is something promising, for sure.
Thanks.
Okay, we have one question more from Eugenio Coronado. Is it possible to grow multilayers, graphene, chromium chloride, graphene, chromium chloride, so stacks of these multilayers?
It's difficult to grow graphene on top of chromium trichloride because chromium trichloride is thermally not very stable. If you increase the temperature above 300 Celsius, it will desorb again from the substrate, from the surface. So at least from MBE, a fully MBE grown electrosharp will be very challenging. But maybe there's also a proposal to combine the glove box transfer with the MBE to have also some materials that cannot be grown on top due to thermal or other constraints, that you can transfer from the UHV via nitrogen box to the glove box, and then maybe prepare the heterostructure that way. That will be one thing, but we cannot do the multi-layers. We did with our current techniques so far.
Okay, thank you, Amilcar. I think if there is no other question, we should move to the next talk. Thanks again. That will be Johann Coraux from Louis Néel Institute.
Okay, I hope you can hear me. And
yes.
Okay. So that's already something. I will then share my screen. So I hope also you will be able to see that. Please, let's check. Tell me if it's okay.
Yeah, it's okay.
You can see the pointer too?
Yeah, we can see the pointer.
All right, everything is fine. So first of all, I would like to thank you all. I mean, to say hello first, and then to thank you all, and also to thank you for this kind invitation to participate to this very interesting workshop. So I've already learned a lot of things. And I think, if I remember well, Manuel asked me to try to step back a bit and try to give you some overview of my feeling on what we could do with synchrotron light here. So I will make basically a very long introduction and try to show you, I mean, how this applies to some of our recent works, and which were done on chromium dichalcogenides. It's a ferromagnetic 2D material. But basically the idea is not to enter too much into details of these results and try to give some overview. So let's see if I can do that, if I manage to do that. So that's as you can see here on this first line. slide, that's a collaborative work between several of our colleagues in Grenoble, Institut Néel. And I'd especially like to stress the contribution from Anneke Probawati here, who was and still is a postdoc at Grenoble, and also from my colleagues Nicolas and Manuel. Manuel was a bit the father of this material because he was the first one working on the bulk chromium dictatorite we've been investigating. So it's a work, obviously, as well, which has been done in collaborations with colleagues here or there in Barcelona, in ALBA, so Lucia and Michael, and also with colleague at Trieste in Elettra at the nanospectroscopy line 2. And I also like to mention the collaboration with the colleagues in China, in Shenyang University over there, Zhang Vito Han especially. Okay, so let me start with, we've already heard talks about 2D materials and ferromagnetic 2D materials, but still I will try to say a few simple things there about these 2D materials. So I know it's very basic and very, almost caricatural what I will say here, but still I will say it. Maybe not everybody is a specialist of 2D materials there. So I put a few important dates there on this slide. So you see first isolation of graphene around 2004 or so. And then this material is of course very interesting for its unique electronic properties. It's a 2D material, and as such, it's basically made of interface or surface atoms. And so you can tune the properties with, for instance, an electric field, which has been used a lot since then on graphene and with other materials as well. So not in 2004, but a few years later, it was also progressively established in literature that graphene, being composed of light elements, carbon, is good for spin transport. So in this sense, graphene would be like, you could say, an inactive spin channel for spintronics, and already you see that these 2D materials are interesting in the prospect of spintronics and magnetic applications. So then a few years later, this is, say, the advent of boron nitride, which turned out to be an excellent dielectric compound material, and also especially suited to sample what has been since then called van der Waals heterostructures. Then we come with moly disulfide and its family of semiconducting transition metal dichalcogenides. So they have unique optical and excitonic properties in particular. And there again, you see back spins arriving. The electric band structure of these materials is particular because they are made of heavy elements, molybdenum, tungsten, and so on. And this brings significant spin orbit splitting of the electric bands. So it's also considered in, I would say, we can say, new paradigms for spintronics, what has been called spin valleytronics, which can be addressed optically additionally. Well, now it's been a few years that we've had very important reports on heterobilayers, where you combine two layers, for instance, two graphene layers, two dichalcogenide layers, and so on, to observe a very large variety of phenomena, correlated phenomena, moire-enriched properties, and so on. So this is by no means an exhaustive slide, but the question was, of course, legitimate at some point to wonder if one could come up with a magnetic lamellar, say, truly van der Waals magnet material that you could exfoliate down to the 2D limit. So we've heard in the very nice previous talk that actually this can be done, and I will tell you a few words about it in a second. So that's the outline of the talk. As I said, long introduction to a very fast-moving field, at least for me. Things are going really fast. I would say two, and that's too fast for me. It's a personal point of view. Of course, I don't expect everybody to share it. And then I will finish the talk with an overview of what we've done and what could be done with a case example, which is a chromium dictatorite, recently discovered material, ferromagnetic material. But I expect what I will tell about this material can apply to many other kinds of 2D ferromagnetic materials or anti-ferromagnetic materials even. All right, so we've already heard about that, these two famous papers. published back to back in the same issue of Nature about the discovery of intrinsic ferromagnetism in chromium iodide here and chromium tellurium germanide compounds here. So these are exfoliated samples. You see two pictures of the samples here. So exfoliated by the usual methods down to the single layer limit or few layer limits. And maybe the important things I would like you to remember on this slide is the Curie temperature. You see there is magnetic order, so ferromagnetism below a certain temperature, which is basically a few 10 kelvins. And this is usually smaller than what you have for the bulk compound, okay? And in the case of chromium iodide, well, you have a very interesting number of layer dependent magnetic properties. So you see here the hysteresis loops. They are measured optically as a function of an applied external electromagnetic field. And you see that if you have one layer or bilayer or trilayer, just because that was the contrary, monolayer, bilayer and trilayer, then depending on just because you have a specific kind of magnetic interactions between the layers, then you have different kinds of behaviors. All right, so you may wonder, and we've already had quite some answers today, why it could be interesting to address and to study this kind of new Van der Waals compounds, magnets. And there is a very nice review about that and other topics published a year and a half ago, which really I recommend because actually, as I said, the field is fast moving. And it's good to have some critical view on the field, and this is precisely what is found in this publication. So I picked up a few items here. The first one is about basic physics questions, especially related to dimensionality. I won't enter into much details because we've heard that in the introduction of the previous talk. So there is something very specific in magnetic ordering in the 2D limit, depending on the kind of degrees of freedom you have for the spins. Well, I already touched that in a way, the next item, which is about optimal electric field control of magnetism. Obviously here you have 2D materials, so essentially made of interface atoms. They are magnetic, and you could try to apply some electric field there to tune the charge current density, and then maybe tune the magnetic properties of the material. So that's, I mean, we've heard that already. This is not a new concept. It has been already applied, for instance, by Dominique Givor and co-workers some years ago at interfaces, not with 2D materials, but with thin films. But there you can see some example here. I think, I don't remember precisely, I think it's with chromium iodide here. You see hysteresis loops strongly modified by the applied electric field in this kind of advanced device that you see here on the side view. And finally, in the prospect, probably more of applications, I already mentioned that you can build Van der Waals heterostructures, okay? And if you do build these Van der Waals heterostructures, then you can think of kind of devices that people are used to work with in spintronics, and as a matter of fact, those that are proposed here are not always very standard for spintronics. But here is an example, two examples. You could think of building magnetic tunnel junctions, and you could also exploit proximity effects. I don't want to enter into too much details here. I give you here a snapshot of what you can find in this publication. Essentially, the reason I'm not entering into too much details here is I have to say I'm not a specialist there. But yeah, these kind of questions, you know, are really exciting our community and pushing a lot of efforts. And you can see really that the field is really, really active. Okay, so now I would like to address, I think, three issues that I think are now clearly identified in the community that come together with these magnetic 2D materials. So the first one is obviously, I think, the stability. And it was realized very early when people were working with chromium iodide, for instance. You see here the exfoliated material exposed to air, and you see that within an hour, the material essentially disappears. So it oxidizes I think this is triggered by light, but it's a very serious issue. So you have, of course, ways to circumvent this problem, and you can, for that purpose, you can cap the material in protective layer with the protective layers, for instance, boron nitride, or as our colleague did in the UMP Thales CNRS, there they deposited manganese oxide on the material, magnesium oxide on the material. Sorry. So means that you need protective capping, but also often when you work with exfoliating materials, you need to work in glove box environments, okay, where you have very few water traces or oxygen traces. Okay, so the second issue I would like to mention, and it's really a crucial one in the view of applications, it's the problem of room temperature operation. It's a very practical problem. Actually, almost all materials that have been reported in the literature to date, they have Curie temperatures or near temperature, if we're dealing with interferomagnets, that are below or well below room temperature. There are few exceptions though, and usually they are, I would say, much debated. So here is an example, a famous one. That's a Nature Nanotechnology paper published in 2018 or 17, I don't remember, 18, claiming strong room temperature ferromagnetism in a monolayer of vanadium diselenide that has been grown, I think, by molecular beam epitaxy. And well, a few months later, you find in this Nanoliterature paper that actually reports results measured by X-ray magnetic circular dichroism that, well, basically they found no dichroic signal in these samples, in such samples. And even when you go down to low temperatures, there is nothing in these results. So the situation in this material is rather uncertain, I would say. I can pick another example, also a famous one, and this is iron germanium telluride. There, these are exfoliated flakes, and I mentioned that earlier. This is put in a kind of a transistor configuration, where you can apply a strong electric field here through an ionic gate. And the reason for that is that if you use an ionic gate, you can apply very strong electric fields and then strongly modify, in principle, the charge carrier density in the compound. And well, this publication, this way, reported that you could tune the Curie temperature above room temperature in this compound. And a year later, actually, with a detailed physicochemical analysis, it was found that what happens when you do this process of ion gating, that you have an intercalation of some of the compound in the ion gate that actually alter deeply the composition of the layer compound. And so at the end, it's not anymore magnetism coming from this compound, but probably some amorphous iron germanide impurity in the compound. So I really want to insist on that. Well, I will tell it again, but you need to know what is the material you're dealing with, and this is often a difficult question to answer. So far, I think things are changing really fast, but at least with a few weeks ago, or a few months ago, the only realization I knew for room temperature operation on Van der Waals compound was obtained on rather thick flakes. So this is here iron germanium telluride that has been exfoliated and shaped in the form of this. You see the scale here of micro objects, and changing the shape, and then the shape anisotropy alters strongly the magnetic properties, and especially allows to reach a Curie temperature above room temperature. And you see, this is for rather thick flakes, 250 millimeters. So I think now, in the quest for MBE grown material, then things are progressing fast, and maybe there are now new compounds that perform at room temperature. Anyway, this difficulty of reaching room temperature operation has pushed a lot of effort in theoretical modeling and prediction. So there is a theoretical screening of some possible relevant room temperature candidates. So I don't know. The first reason why is that I'm not a specialist of these initial calculations, how reliable you can take these estimates of the Curie temperature. But you see there are a number of compounds. The question remains open whether the materials are stable in our conditions, they are naturally occurring or not, or if they can possibly be sensitized. But there is definitely plenty of room there, probably. So the last issue here or point was already addressed in the previous talk. It's about the direction of magnetization. So there are indeed, as it was said, almost all the compounds, they have perpendicular magnetic anisotropy. The magnetization tends to point perpendicular to the layer. There are exceptions, though, especially in the case of antiferromagnets. So we already heard that a moment ago. These three atomic compounds as well. And I already mentioned in the previous slide that you can have, if you select, if you shape the materials in the given configuration, then these films here, which naturally would have otherwise a perpendicular magnetization, have the magnetization which goes into the plane of the sample, and they form, as you can see here, some kind of flux closure patterns. Okay, so these, by the way, were measured at a synchrotron, I think in the US, with a combination of X-ray magnetic circular dichroism and photoemission electron microscopy. And I will actually come back to that because this is one of the needs we have used to address our materials. So why is it interesting? We've heard that in the previous talk. You, for instance, would like to be able to test these famous XY 2D spin models. You may also be able to assess the particular quantum phases via proximity effects in heterostructures if you use one of the van der Waals compound that would have an in-plane magnetization. And you could also think of building kind of synthetic antiferromagnets only based on 2D materials. All right, so as before I switch to an overview of what we've done, I'd like to make an intermediate conclusion on what we need and want in the context of the study of these materials. So the first thing we would like to know is you want to make sure what the structure and composition of the compound you're studying are really, actually. And this is not a simple question at all. This is an essential question that if it would be addressed unambiguously would allow to avoid a lot of debates, I would say. Then you would like to be able to relate the structure, electronic and magnetic properties. And I think to some extent, we've heard a few questions in the previous talks that were suggesting we should go in this direction. You probably would need also elemental selective information, especially regarding magnetism. Otherwise, you can be tricked, I would say. And at least from our perspective, we would like to have specially resolved information. So one reason relates to what I've already said. You might have some issues or open questions regarding the structure and composition. So you need to be aware that you might have spatial inhomogeneities on your samples. Plus, you can of course address full area samples grown by MBE. So with a full calibration of sample. But it's still the case in this community that many materials are produced by mechanical exfoliations. So they are tiny flakes, a few microns or a few 10 microns on the base cases in extension. And so for that, you need specially resolved information. Okay, so let me now switch to what we've done actually. It will not only be about what we've done, but mostly. So this is, to me, a case example. That's magnetism in a chromium dictatorite. It's one of these transition metal dichalcogenides. It's not a semiconductor. I will come back to that. Okay, so this is based on this work that we published last year, together with colleagues from ALBA, actually. You see Lucia and Mihail's names here. So chromium dictatorite. So this is a material we had in the cupboards in the lab for a few years. And our colleague Manolo came to my office one day and said to me, well, okay, maybe it's interesting. You know, there have been interesting papers published in Nature recently. Maybe we could have a look at this material because it's ferromagnetic at room temperature. So we obtain it. I will tell you how in a second. But most importantly is that we obtain it in a particular crystallographic form. Okay, so the material is polymorphic. You could have 2H or 1T polytypes. So you need to have this one. And also, if you mix chromium and tellurium together, you can have different compounds. So you have chromium telluride, not dichalcogenides, just single tellurium atom, with a TC below 200K. This is a side view of the structure. You see it's a bit different from this one. You have chromium 2, tellurium 3, with a TC that can vary from below room temperature to very close temperature, but it's actually not exactly what we can call a van der Waals material. You see there are bridges between the different layers, and it probably doesn't make it easy to exfoliate the material. So these are chromium bridges, as far as I know. So we need to be able to select this here, to have a process that allows us to produce that. And the way we do that is to use synthesis of in the bulk form of this compound. So we put a molar mixture of potassium, chromium, tellurium in the glove box. Then we seal that in the quartz tube, which has been evacuated from any contaminant, and we leave that for several days to a high temperature and cool down slowly. And then you need to be careful when you handle that. You need to open the quartz tube in the glove box, because there is potassium intercalated in the chromium telluride layer. And if you don't, then there will be intercalation that basically will transform your material into a dust. And finally, you use a reaction, a special kind of reaction to eliminate, to de-intercalate the potassium there. So we believe that the potassium is very important in the process because it's an electrodonor species, and it provides a lot of electrons to the surrounding chromium telluride layers. And we believe it stabilizes the 1T phase to the expense of the 1H or 2H phase, if you want. So that's not an easy task to obtain the compound you want, but once you have it, it's in the form of this kind of tiny crystals, micron scale. So this one is not the biggest one we get, but you will not have centimeter scale like that. It's more a few millimeters. And then we exfoliate that. So I won't enter into too much details here. I heard plenty of experts of exfoliation of 2D materials. We use different strategies, PDMS, viscoelastic stamp, thermal resist tape, Scotch tape, etc. So far for us, Scotch tape proved to be the best, and we use different substrates. So that's a minor point, but sometimes it's important, maybe at least to mention it once. We need, for some of these experiments I will show you today, some conductive substrate. Okay, so this guy here is optimal, as you can see, for the contrast, the optical contrast, and it allows you to find out the thinnest flakes. This one here, less suited, but it's needed for photoelectron microscopy experiments. So we can do basic stuff, just exfoliating with a Scotch tape on a SiO2 substrate, or we can do more advanced stuff, like exfoliating chromium ditelluride, exfoliating graphene, and then putting one on top of the other. You see here, maybe there is the chromium ditelluride, and this is a large graphene layer. And we can put that on a substrate with markers, called markers, to easily locate the region where we want to work. Okay, so what I discussed a few slides ago, that I just showed you, was about exfoliating chromium ditelluride plates. There is another strategy, and this is somehow related, even though it's not about the same material, it's related to what we've heard in the previous talk. You can also consider actually growing the material on a substrate and growing with the thickness that you want. So people do that with CVD and with MBE. These are the two papers I show you here. Well, you see this work here is a careful one, where it was advised that maybe it's not purely chromium ditelluride, but chromium ditelluride with some bridges, so not often or always a truly lamellar material. This work here does not address so much these kind of questions, but what I can tell you is that the chemistry and properties of and structure of these materials still remain a bit debated. So the composition, for instance, in this work is highly uncertain. But I think it's important to stress this kind of work because there is definitely an ongoing effort and a strong one worldwide with a really high expectation to grow these materials with the desired thickness and quality. So coming back to our results, I will start to show you a few of our work actually on exfoliated chromium dictatorite. You see here atomic force microscopy topographs with a rather thin flake, 10 nanometers in thickness, and here a thicker one. And we put these guys in UHV, in the UHV chamber, for instance, at CRC, ALBA and nanospectroscopy in Electra, and had a look at them with X-ray absorption spectroscopy, X-ray photoemission spectroscopy, and outside of the UHV also with Raman spectroscopy. So it's striking to see that if you exfoliate a fresh flake and have a look at it with XAS or XPS, you have the blue curves, okay? And regarding Raman spectroscopy, the blue curve as well. But if the sample is let out for a few hours or days in air, then this is not the same thing anymore. So the material has changed. You see you have an additional signal here as well. The Raman signature has changed deeply. And well, all these techniques here, especially XAS and XPS, they are very sensitive to the very topmost surface layers. And so they tell us that the top of the material is actually oxidized. We know it's not going deep inside the crystal because we have some magnetic imaging I will show you later. But at least we should be aware that the top layers are oxidized. It's a slow oxidation, but it's there, and it should not be disregarded. All right, so here I'm showing you two XAS spectra measured on this specific flake here that we exfoliated and had a look at with AFM. You see it back in the photoemission electron microscope in the Electra or ALBA. And what we do is we can measure on the full image here, tuning the photon energy. We can measure, I don't know, point by point on this image, extract point by point on this image some XAS spectra. Okay, and you see they are obtained here on different regions of the sample. They are slightly different. We also see exactly the same kind of differences where you change the polarization of the X-ray beam. So what we have here is a dichroic signal. You can extract, so this is all room temperature measurement. It's a tiny signal, but it's there. And you can extract the difference here, point by point on this image, and this is what you get at the two different energies here, and here. Okay, here, sorry, and here. There. Okay, and you get here something which is related to the magnetization of the material. Okay, so you see basically the projection, the color shade here, the gray shade tells you about the projection of the local magnetization against the direction of the beam. And well, you have different contrast, opposite contrast if you measure here or here. So that's one configuration. We had a look here at another flake, I think, or the same flake. This is the same flake that for which we applied a magnetic field here to reorganize the magnetization pattern in the flake. And you see here you have a flux closure pattern with an in-plane magnetization. Here I should insist this is in-plane magnetization for a flake which is a few 10 nanometers in thickness. Okay, so what you can do is compare what we have here to results we obtain in the lab. This is magnetic force microscopy. There we don't sense directly the local magnetization direction, but rather the stray field that is emitted by the magnetization texture. And we're actually able to establish a 1-to-1 correspondence between these images. What we see actually in MFM, you see this is a profile on these domain walls. Across these domain walls, you see these kind of functions up and down above the average value. It actually tells us, I won't enter into details, that the magnetization is nail-like domain walls. The domain walls are of nail type. Okay. So we can even, with a nicely resolved image, measure the profile, how the magnetization evolves when it across the domain wall, and that way we can estimate domain walls which are typically 50, 70 nanometers thick. All right, so here what I'm showing you here is a set of flakes that were exfoliated and measured in the beam with XMCD as a function of temperature. And what you see is that the domain structure is vanishing above 310 or 15 Kelvin. And when you cool down, then it comes back. So there is no, you see that the domain structure is unrelated after cool down, no significant magnetic memory, and a Curie temperature around 315 or so. That doesn't seem to depend so much on the thickness of the material that we addressed. So with that, I would like to conclude. I think it's important to keep in mind that both exfoliated and full layers need to be investigated. So far, it's a strong need from the community, I would say. We need to make sure that the material we are looking at is not oxidized and it has the right structure. And I think that the tools we have at synchrotron facilities are really useful. I didn't mention so much what we could do with diffraction, but probably there's important information we can get from that. The temperature dependence is obviously something we need to study, and the bad point is often below room temperature. So XMCD beam lines are especially suited for that, but when you want to couple that with imaging, it's getting more complicated, even though you can still do it at decently not too low temperatures, I would say. But then you would like to address many dependencies of the properties as a function in these films or flakes. What happens when you change the magnetic field? You would like to do that in situ, which is possible with some special sample environment, I know. You would like to address the thickness dependence, strain dependence maybe, that we've heard about that in the very first talk, I think. The electric field dependence is also something definitely you want to address. So I think this all calls for, to some extent, some developments at the different beam lines. The spatial resolution is certainly very important there. And the best resolution we get, the better. That's difficult with X-rays, I know. But at some point, we will be interested in having resolution approaching 10 nanometers or few 10 nanometers. And I didn't mention that so far, but there are many things we would like to do also with relating what we observe in magnetic properties, in terms of magnetic properties, with, I don't know, other excitations in the material. So electronic, phononic, magnonic. Here you see, for instance, the electronic band structure calculated for chromium dictatorite remains to be verified experimentally. And, well, I think I already spoke too much, so I would like to apologize for that. And thank you for your attention.
Thank you very much, Johann, for your talk. So it's time for questions. Maybe I can ask you one, as you are an expert user for beam. How would you like to have a beam, or what would you like to have from a beam to have a better result, or in what direction do you think the beam should go if you want to fulfill the 2D materials?
I think we need to, most often, we will need lower temperature than 300 Kelvin. So I think we can reach, we can cool down the sample environment with liquid nitrogen and go below room temperature. So that I think this is something we cannot avoid for many of the materials. We will need that. So I think it can be done. I know it's long. You need to let the system stabilize for a long time, and so it makes the measurement longer. But that's certainly something we would like to do. And then what I wrote here is important. We need specific sample environments to be able to play with the magnetic properties. So the magnetic field, I think, is possible already with specific sample holders, but the strain dependence, having piezoelectric substrate, for instance, or being able to apply an electric field is something that would be very interesting as well.
Okay, so more flexibility in the environment of the
sample environment we need to play with. Then there are practical details about which are maybe not so anecdotic with the preparation of the samples. So we've heard about transferring samples grown by MBE with a suitcase, which is obviously a good way. You could think of capping strategies as well with materials that you can degas in UHV. And I know that there are some XMCD beam lines where they couple the UHV system with a glove box. So you can imagine preparing the material by the exfoliation and directly entering it into the UHV system without seeing air, which are things that could also be bring a lot of flexibility.
Thank you. We have one question. The question is, what is the maximum thickness of the 2D chromium telluride film we are looking at for the optimal sample functionality?
So the minimum thickness or the maximum thickness? I mean, the maximum, it can be very thick, but the minimum thickness, I mean, we have the feeling now that at least for until, I mean, down to 4, 5, 6 nanometers, the system is still in plane magnetized and at the room temperature, Curie temperature. So it's work in progress. We are exfoliating better and better the samples, I would say, with time, but it's not so easy as with other 2D materials. So we will see how thin we can get. If we can reach the few layer limits, 4, 5 nanometers is already rather thick, thin. It's 7, 8 layers also. So maybe we can go to 1, 2, 3 layers and see. So we're trying to do that.
Okay, thank you. So I don't know if there is any other questions. Well, if not, okay, yes, there's another one. From your slide, do you imply that formation of transition metal dichalcogenide monolayer onto graphene substrate at room temperature will exhibit unstable properties?
Unstable properties, I'm not sure I understand what it's referred to. People, I mean, graphene is obviously a substrate of choice, graphene on silicon carbide, for growing magnetic, ferromagnetic 2D materials. So there are several attempts in this direction and some are successful. So by unstable, I'm not sure what we refer to here.
Electronic and magnetic defects. Instabilities in electronic and magnetic defects.
So the stability, well, I don't know what the question implies. Actually, the materials, when you operate them in air, they might be unstable. That's of course the case. Then if we refer more to the magnetic properties themselves, if they are sensitive to defects or to dimensionality effects or whatever, then this is another question. So there will be defects in the MBE grown materials. Depends on the density of defects, it might be a problem. I don't know. That there was the question already in for the previous talk. If you have large domains, I don't know, several hundred nanometers large, then maybe you have enough to play with large patches of a given magnetic phase. But if you have much more defects, then you might not obtain the phase you want, the magnetic phase you want to have. But I know it's a very vague answer I'm giving here. I'm not sure.
Okay, I think if there is no more questions around, yeah, Manu, please.
Very nice talk, Johann. Very simple question. So for building heterostructures, the typical procedure, and probably the more reasonable, is to use flakes produced or fabricated by exfoliation from bulk materials. Do you see opportunities in trying to do that from single layers grow via MBE?
Yeah, I think there are opportunities there, and even pure recent papers where people grow materials by CVD MBE and exfoliate them like that. So it's probably, yeah, probably there are nice things to be done there. You need a good substrate. Good meaning that it doesn't stick too much to the materials you're growing on it to be able to exfoliate it. So yes, probably there is work to be done there. And also you could think of using exfoliation on full substrate that are relevant, like a graphene substrate, for instance. You could exfoliate on that, or the contrary.
I think Amilcar wanted to do a question, please.
Hi, very nice talk. So I have a question related to the anisotropy of the system. So you mentioned that this in-plane anisotropy, but have you quantified the anisotropy fields, for example, to see if you reduce the dimensionality, how you will, how it will project when you try to aim to go to the very thin limit?
It's a difficult question, but an important one for us. So the reason why we believe the system is in plane, the main reason is the shape. It's obviously the shape anisotropy. So the dipolar energy of the system would like to be minimized, and it's the case when the magnetization is in the plane of the sample. But if we make this assumption and try to measure, which we've done, some hysteresis loop of the bulk compound, we already see that there is some in-plane anisotropy, but it's not sufficient to consider the dipolar energy to understand that, meaning that there is something else, and there is an intrinsic magnetocrystalline anisotropy, which we believe is out of plane. Okay, so there is a competition between two effects: the magnetocrystalline anisotropy pushing the magnetization out of plane, and the shape anisotropy pushing the magnetization in plane. So what I cannot answer to you is what will happen when we go to the very thin limit. Who wins? So that's an open question. Maybe chromium dictatorite will be interesting.
I see.
Maybe for you also to have this kind of XY behavior, but we don't know. We need to address that.
Okay, thank you very much.
Thanks.
Okay, then thanks again, Johann, for your talk. If there is no question, we will shift to the next talk. That will be Debora Pierucci from Center for Nanoscience and Nanotechnology, CNRS, in Paris. So Debora, please.
You can hear me?
Yes.
Okay, I will try so at first to share the screen and see. You see it?
Yes, we are seeing it.
And you see also the arrow of the mouse?
Yes.
Okay, perfect. So good morning, everyone. And I would like to thank Miguel, Manuel, and Massimo to give me today to participate to this interesting workshop and give me the opportunity to present my recent result on this new kind of 2D materials concerning the ternary alloy of transition metal dichalcogenide. In particular, today I will show you most of my results are concerning the electronic structure, so the band structure of these materials uncovered with the angular resolve for the emission spectroscopy. So let's outline my talk. At least I will summarize briefly the standard properties of the properties of standard TMD's materials. So in particular, optical and electronic properties, in particular, giving particular attention to the band structure of this material and their evolution as a function of the number of layers. Then we'll see how we can tune and add the new functionality to standard TMD by creation of alloy. We will see how we can obtain this alloy, in particular via chemical vapor deposition, and see the structural property of this system. And also, and we look inside the optical electronic property of this ternary alloy as a function of number of layers, also the composition. So one of the interesting family that we see today in the other talks also, interesting family of 2D material is the one of the group 6 of dichalcogenide MX2 materials, which are formed with one layer of this material are formed in fact by one metal, the transition metal atom, so can be molybdenum or tungsten. That is bonded to 6 chalcogen atom that can be sulfur, selenium, or tellurium in this trigonal prismatic structure. From the top, we recognize this hexagonal structure that correspond to an hexagonal Brillouin zone in the reciprocal space. So these materials, as we know, they possess property that depends on the number of layers. In particular, theorists tell us that the character of the orbital at the top of the valence band and the bottom, the conduction band, are very sensitive to the interlayer interaction. Is the reason why, when we change the number of layers of these materials, also we modify the electronic structure. In particular, concerning the band gap going from the bulk until to the monolayer, what we see that we increase the band gap, but also we change its nature. Until the bilayer, the material, the TMD standard TMD present an indirect band gap, this band gap becomes direct in the case of monolayer materials. This is a very interesting property. In fact, when we have a monolayer, we have a very enhanced PL respect to a bilayer material, where this signal is almost 1 order of magnitude less. That means that these materials are very interesting for optoelectronic application. In particular, they have a direct band gap in the visible spectrum, ranging from 1.6 to 2 eV, depending on the type of TMD that we are looking. If you look at the system, so this system of standard TMD, so the inversion symmetry of the system is located between 2 layers. That means that in the monolayer, the inversion symmetry is broken. This inversion symmetry is recovered every time we have an even number of layers, so bilayer, 4 layer, and so on. Due to the strong spin orbit coupling that we have in the d orbital of the transition metal, at the K point of the Brillouin zone, we have a splitting of the band. In particular, in the monolayer, where the inversion symmetry is broken, the degeneracy of the spin at the K point of the band is left. So we have spin polarized band with the spin texture of out of plane. Concerning this, the contrary, in the case of the B layer, the bands are split but are spin degenerate due to the presence of this inversion symmetry. At the gamma point of this system, the bands are spin degenerate, but we have, due to really sensitive nature of the orbital, here, they are out of plane orbital that form this band, then are very sensitive to the interlayer interaction. We have this splitting of the band when we increase the number of layers. And this is very nice because it's very useful to recognize when we are looking at the electronic structure of this material, if we are looking for a monolayer or a bilayer. So now let's see how we can modify and introduce new functionality in this standard TMD if we create an alloy. In particular, the alloy that I will talk about is when we manage to create a TMD between a transition metal, transition metal, and 2 different chalcogenide atoms. In particular, in the case we manage to replace completely all these line of chalcogen atom with another chalcogen atom, we have the prototypal ternary alloy named Janus TMD. So due to the fact that we have 2 different chalcogen atoms now, these chalcogen atoms have different electronegativity. That means that we have in this system an internal electric field that broke the mirror symmetry that we have in the monolayer system. And this broken of the mirror symmetry introduced, so allowed to remove the spin degeneracy of the band that we have at the gamma point, with a splitting of this band in opposite direction in the momentum space, what is called the Rashba effect. So this is very interesting for a possible spintronic application of these materials. Another important thing is that the theory predict for this material, as for the standard TMD, a direct band gap at the K point of the Brillouin zone. This is interesting because in the case we can also modulate, so the composition of this alloy and the relative composition, the relative ratio between the different chalcogen atoms, we also can modulate, so the band gap, the direct band gap of this system, and we have this linear variation of the band gap. In particular, for an example, for this alloy of tungsten, sulfur, and selenium with different composition of selenium, increasing the selenium composition, we see that we can range, we can have band gap going from 600 nanometer to until 750 nanometer. So this is band gap engineering is very, very interesting in the point of view of optoelectronic application of these materials. In particular, another property that we have that is predicted by theory, and we have if we modulate the composition of this ternary alloy, in particular in the case of the alloy formed with tungsten, selenium, and tellurium, is that when that modulating the composition, so changing the concentration of tellurium, we can induce a structural phase transition. In particular, we can go from a standard trigonal prismatic phase, that the phase that we have in the standard TMD, to a distorted octahedral phase. This is very interesting because, how you can see here, for a tellurium composition, so about 0.58%, the barrier to go to this other stable configuration is 0. So this transition is possible, tuning the composition. It's very interesting because related to the structural phase transition is also the theory predict that is related topological phase transition induced by this band inversion at the gamma point between the pi band of the chalcogen atom and the D band of the transition metal, giving rise to a quantum spinol insulator with a very huge band gap, about 100 of milli eV, which make this material very interesting. So until now, at my knowledge, this phase transition is was only measured for standard TMD. There is no, in the literature, for my knowledge, this measurement transition for the ternary alloy. So now the question is how we can obtain this ternary alloy. Our choice was going to do this with the chemical vapor deposition. This technique, as mentioned before, is a very useful technique to obtain huge size of our flake. In particular, a chemical vapor deposition setup is formed with this quartz tube, where inside a different position we can locate our precursor, in our case our powder of tungsten disulfide, the tungsten diselenide, inside this furnace. So when we raise up the temperature of the furnace, inside here the tube we have a gradient of temperature. This is very interesting because tuning the temperature and tuning the position of the this precursor inside the tube, we can tune then quantity of the ratio that we have between selenium and sulfur, and so we grow different composition alloy with different composition on the substrate that usually use is SiO2, so silicon oxide, that is put here downstream. So the typical flake we obtain with this technique are triangular, and the huge part of them are monolayer. With atomic scanning transmission electron microscopy, we are also sensitive to the atomic number contrast. That is very useful because we allow us to recognize this hexagonal character or organization of the atom, and we also see from the different contrasts, we see in particular 3 different contrasts on the image, where are located the different chalcogen atoms. In particular, where the contrast is lower, we can say that we have a selenium on top, a sulfur on top of selenium. When the contrast, when the contrast is the lowest one, we have the sulfur on top of sulfur. When the contrast is medium, we have the sulfur on top of selenium. And when we have the brighter spot, we have the selenium on top of another selenium atom. So this, in particular, all the grown of our flake, the flake that I will show you the data now, are grown by our collaborator in China at the Yunnan University. So we say that most of the flake have this triangular shape and are monolayer, but this is true. This is true on our substrate. They are mostly like that, but depending on the position of the silicon substrate in exposing to the different flux of our reactant, we can have on the same substrate also a flake with other different shape, this hexagonal shape or triangular truncated shape. This is related to the grow process, in fact, and to the kinetic of the edge that are forming this ternary alloy. In particular, in this kind of material, the stable edges that we can find are of 2 types. We have the chalcogen zigzag edges or the metal zigzag edges. These different edges depend on the partial ratio between the chalcogen atom and the transition metal atom. So when we have when the partial pressure, the metal concentration exceeds the stoichiometric ratio, what we see that the more stable edges, so the kinetic of the edges is in favor of these more stable zigzag metal edges. So in this case, we have this triangular flake. In case then we have a partial pressure of the chalcogenatum, the partial pressure of chalcogenatum and the transition metal that are in the same stoichiometric ratio, what we see that we have an equal probability of the two edges. So we have this hexagonal shape. As we see also from the optical image that I show you here, we see also different contrast on this kind of flake. That means that probably, for sure, that we see later, we have different layer of material, so 1, 2, and 3 monolayer in particular. So having also different layer means also that we can have different stacking of these multi-layer materials. In particular, the optical image can help us also to recognize the different type of stacking. In fact, when we have two rotated triangles, we are in this hexagonal stacking, 2H stacking, in which we have the transition metal on top of the chalcogenatum and vice versa. So this is, remember us, if you are familiar, the ALBA stacking of graphite or graphene. In case we have this aligned triangle, we have in this 3R stacking, in which we have so the chalcogenatum on top of the metal, but the other transition metal, the other chalcogenatum are slightly shifted at the center of the hexagon. And this, remember, if you are familiar, the ABC stacking that we have in graphene. So now let's have a look to the optical property of this system. In particular, for our study, we obtained three different alloy with three different alloy between tungsten, sulfur, and selenium. So we vary. There was a variation of the composition between the two chalcogenatum. We fixed the transition metal. And we grow three different alloy with the three different concentration of selenium. As we can see, so we find this linear variation of the band gap as a function. This is a PL spectrum obtained with a laser excitation of 532 nanometer. What we see that clearly we have this linear variation of the band gap as a function of the increasing of the selenium concentration. What we see also, if we compare with the PL signal of the pure material, so the tungsten diselenide and the tungsten disulfide, we see that we have almost the same sharp peak, and we have no signal nearby the signature of the pure material. That means that we really create an alloy without any domain of the precursor, so a single precursor. And now what we do also, we study the evolution of the PL in this material as a function of the number of layers. And what we see that we have, as for the standard TMD, a similar behavior. So the PL decrease as we increase the number of layers, because we have, in principle, an indirect band gap for the 2 and 3 monolayer. But what we see clearly that when we increase the selenium composition, the PL for the 2 monolayer are very huge. This is strange for this kind of materials, if we remember the standard TMD. So we try to understand a little bit to evaluate this. So we normalize all the PL spectra to the maximum of the PL that we have in a monolayer, and we compare the value. So what we see, until 40% of selenium, we see that we have similar behavior of the PL for the 2 monolayers. So when we so the PL of the 2 monolayer is almost 1 order of magnitude less than the PL of the direct material, so the monolayer. When we increase the composition of selenium, we see that we have this strange behavior. So here, for the 50%, the PL decrease only of 5 times, and here only of 2 times. So we try. So there was something different in these two alloy respect the standard materials. In fact, also, if we look at the shape of the PL peak, is also larger, indicating that probably we have more than one component that contribute to this signal. So we try also to understand if it was a relation related to the stacking. So, and then we analyze also different flake with different stacking. So we have the 3R stacking and 2H stacking. Here, what I show you is an intensity and deposition PL map. What we saw so by optical image is real, so we have really different layers of our TMD, and as is clear that here at the edge we have one monolayer that is the intense one, the signal is the intense one, and then going inside the flake where we have increased the number of layers, we decrease so the signal. But what we see if we look at the integrated spectrum, so for the two stacking, also the situation is similar. The intensity of the PL of the two monolayer is really high, respect the normal and the standard TMD materials. So the next step was, let's try to look really inside the electronic structure of the material, their band structure. And to do that, we use a very powerful technique that is the photo emission, the unresolved photo emission spectroscopy. In particular, we went to Antares beamline in Soleil, where they have a very small beam, around 500 nanometer, that allowed to also locally find our flake on a substrate. In fact, in this beamline, we can map our sample, we can do this nano XPX map at the edge of the two components that is present on the sample, so for example selenium or tungsten, and we can really localize the flake on the substrate. So here I show you also the integrated XPS signal from 1, 2, and 3 monolayer. So the different contrasts in fact indicated the different different layer that we have on the material. So as we see here, the selenium 3D present only one peak. We have the splitting of this doublet, standard one, but we have only one component. On the tungsten, we see two components. That is reasonable because we have a tungsten linked to a selenium and the tungsten linked to a sulfur. So in particular, the component linked to the selenium is higher. That is related to the fact that we have a huge percent of selenium in this alloy. So now that we locate the sample, we know exactly where to go. We can perform a valence band map in these three different positions. And here what we show you, so the condition was 100 eV at low temperature, the same as for the XPS map. And what we see here, we see the different map, the different valence band map for the 1, 2, and 3 monolayer. As I told you, very useful is the evolution of the band at the gamma point. In fact, here is only the derivative. So is the derivative of the signal that allowed us to enhance the contrast of the band and look better at the fine details inside the band structure. So as we can see, for the monolayer, we have only one parabolic band at this gamma point. For the bilayer, we have two bands, for the 3-layer, 3 bands. So really, we are looking for this different stacking of this ternary alloy. If we have a look more in detail at the different properties. So as I told you, at the K point, so the predominant nature of the band is due to the outside orbital, DZ, the PZ orbital of the chalcogenide and the transition metal. So they are less sensitive to the interlayer interaction. And this splitting that we have here is induced only by spin orbit coupling. So we can see that the value of the spin orbit coupling see an evolution from 1 to a 3 monolayer, going from 500 millieV to 380 millieV. That is at least a very huge value compared to the transition metal dichalcogenide. Another interesting thing is how the electronic structure evolve and the position of the top of the valence band evolve as a function of layer. In fact, for the monolayer, the top of the valence band is located at the K point. When we go to the bilayer and 3-layer, this top of the valence band is displayed, go to the gamma point, as we can see. Also change the difference that we have between the energy of the top of the valence band at the gamma decay point. Here is only 500 millieV, is almost the same, 480 millieV. But what we see a really peculiar structure concerning our two monolayer 80% selenium alloy. In fact, even if the top of the valence band is at the gamma point, the position of the valence band at decay point is really close. So now, in order to understand better the behavior of this material, we need a little bit of theory. So we perform DFT calculation in order to see also the evolution of the conduction path. That we can help us to understand better the optical properties. So as for the standard TMD, so the monolayer is a direct band gap. We see here, so the top of the valence band is a decay point, the bottom of the conduction band also a decay point. For the trilayer, we have the top of the valence band at the gamma point, an indirect band gap, because now the bottom of the conduction band is between the gamma and decay point, this lambda or Q point of the band structure, so indirect band gap. What happened here for the bilayer? For the bilayer, in this case, the opening of the cause of this peculiar behavior is, the theory tells us that depending a lot of the opening of the pz orbital of the selenium atom. In fact, this opening tends to increase the position, increase the value of the valence band here at the gamma point, but also decrease the position of this of the bottom, the conduction band between the gamma and decay point. So what we have here, we have a sort of a very mixed situation, because it's true that the top of the valence band is here and the bottom of the conduction band is here. So we have an indirect band gap, but these 2 points are really close. That means that also this intermediate, so this transition can be allowed. And this is the reason why we have this huge PL and also this increase of the shape of the PL peak. So what I will show you now is a very, very recent result. We obtained this at the beginning of the year, and we try in particular to look more in detail to the electronic structure of the monolayer of this ternary alloy rich in selenium. Here what I show you is a 3D cut plot in the K-space, where we compare our ternary alloy and with the reference sample. So in the same condition, in order to understand better our data as a reference, we also in the same condition, we measure a standard TMD, tungsten disulfide. We allowed us to understand better our data. So what we see if we cut, so along the gamma K direction, as before, we see, as expected, as we see also for the alloy, one parabolic band for the standard TMD and one parabolic band for the alloy. But the difference happens when we cut along the gamma M direction. In fact, in the case of the gamma M direction, for the standard TMD, we have only one band. For the alloy, we have a split in the momentum space, so along this gamma M direction. This is very interesting, and that means also that the symmetry that we have here in the standard TMD is not available for our alloy. In fact, here we have only one mirror plane that is passing by this what we call gamma K1 prime direction, and we have this splitting of the band along this perpendicular direction, so the gamma M direction. So now let's try to understand what happened. So we are, let's have a look more in detail. Here I show you the iso energy cut of this 3D shape of the band dispersion. What we see clearly that here we have only one paraboloid, so it's the standard TMD, and here we clearly see two paraboloids that are shifting along the KY direction, so the gamma M direction. So why? We have this peculiar behavior in the ternary alloy. So we understand, we saw that this paraboloid for the standard TMD is spin degenerate and is the standard behavior, what we see. We expect, for example, in the case we have a perfect alloy, but is not our case, that we have this electric field directed out of plane that break the mirror symmetry that can induce so this Rashba splitting of the band at the gamma point. But in the case of the conventional Rashba splitting, the band are uniform splitted in the both direction, the kx and ky. So we have this peculiar shape that if we make a cut, iso energy cut, we expect to see two concentric circles. That is not our case. In our case, clearly we see two paraboloids that are shifted in the y direction, and this behavior can be induced by a electric field that is orienting along the in-plane direction, in particular parallel to the kx direction. So is our case. In our case, we have a unidirectional out-of-plane Rashba splitting. Why out of plane? Because in this particular splitting, the band are polarized out of plane, so like in the K point of the Brillouin zone. So there was really an open question, and this is still an open question. Now we have all the hypotheses that we have to verify, because we don't know why this particular material possesses this in-plane, peculiar in-plane electric field. What we can do, we can evaluate the Rashba parameter given by the difference between the delta K, the splitting in momentum and energy, giving us a very huge value of the Rashba parameter. That is, if we compare with metal or quantum dot, is very, very huge. That means that we have really a giant Rashba splitting that is very, very interesting for spintronic application. So in order to understand a little bit why in this material we have this in-plane electric field, we try also to understand its structure. So we perform PL measurement. Here we have the map of the intensity and the map of the peak energy. We see that the map are almost uniform. The only sizable change that we see is here at the edge. The edge in particular, this metal zigzag edge that we know that can induce strain in the material. And here also what we see clearly, probably is not really clear, but we have the arrow, we see also an decrease in intensity of the PL induced by probably crack that are starting from the edge and going inside the flake during the grow, following the threefold symmetry. So also this crack can induce a strain that can reduce the intensity of the PL. What we know exactly, thanks to the nano ARPES, is that this edge, the zigzag edge, is oriented along the gamma K direction. So is orienting along the direction the field must be oriented in order to generate this split, unidirectional Rashba splitting in this gamma M direction. So the idea is that there is a link between the structural property of this material and the orientation of the in-plane field. In particular, probably this tensile strain induced by the edges linked with also with the strain internal that we had to the fact that we have two different chalcogen atoms with two different electronegativity can induce this preferential orientation of the electric field, so orientation of the atom along parallel to the edges. So in principle, what we think that we have a material with the possible three domains in which the polarization is oriented parallel to the unique edge of this part of the triangle, and so the unidirectional Rashba splitting is perpendicular so to the edges. For sure, this is only an hypothesis because we need to confirm the presence of this polarization domain. What we would like to do for sure next is to do PF measurements, so in order to really visualize the polarization in the plate on the flake, and really also plus will be if we can do also spin resolve ARPES measurement. But you can understand in the case of flake and the setup they are currently available at the synchrotron is more difficult, so to perform also spin resolve ARPES measurement. So to conclude, I would like to thank all my collaboration at the two material team at the C2N, so Abel Karim Wergui, Julian Shast, Philippe Oler, also the postdocs Irene Hernandez, Lama Khalil, also Gilles Patriarche for the theme analysis and Marco Pala for the DFT calculation. Also collaborator outside the C2N, so Pavel Dudin, Jose Avila at the Antares Beamline Synchrotron, the group of Ali and Penn at Union University, Federico Bisti at the University of L'Aquila. I also would like to thank the ALBA Synchrotron because part of this project was financed by the in-house project that I get when I was the previous years beamline scientist there. And at the end, I would like to thank you for your attention.
Thanks, Debora, for such a nice talk. We are very late, but I think we have time for a couple of questions. There is already one question, and it is in case you have a Dressel house plus a Rashba effect, it will produce similar splitting as you obtain it.
Yeah.
Have you considered this possibility?
Yeah, the calculation effect, yes. What's this unidirectional Rashba splitting is similar to what we must obtain with the combination of these two effects. It's true that more calculation is going on by Marco, but you understand that it's not super easy because we have this system with these disorder atoms, and we try to understand why we have this preferential order, this in plane electric field. So yes, it's going on. The study of this part.
So one more question, or Noel?
I have a question, Deborah. So so far it looks like your interest is mostly on non-magnetic materials, but also this Rashba field, no, that you can introduce internally in the materials by going to the, I think it's correctly to say Janus type, no, of system, no, that can also be very important for shaping magnetic properties. Do you have anything on mind or some ideas?
You mean to couple with magnetic materials?
Yes.
Yes, can be an idea to see the coupling. Yes, or you know, now that we have all this material that we can exfoliate, the material that presents the other, for example, Johann present before and so on, we can try to combine them. So in our case, I didn't mention, but the CVD flake can easily transfer on other substrate. So by a wet transfer or that we manage very well. For example, for the ARPES measurement, I didn't tell you, but I need to transfer the flake on graphene because otherwise the SiO2 is insulating, so it perturbs a lot the measurement. So yes, is not one of the main direction that I'm going now, but yes, we can try to transfer this material on other ferromagnetic materials and try to see the interaction and the evolution of this Rashba interaction. Yes, for sure.
Thank you.
Okay, then if there are no more questions, thanks again, Debora, for your talk. And then we move to the next talk that will be Massimo Tayarida from ALBA, that he will talk about ARPES capabilities at ALBA. Hello, Massimo.
Yeah, hi. So let me start to share the screen. I think this should be. Okay, I will try to be very fast also, okay, to try to recover a little bit of time. So this is mostly to show you the beamline that we are constructing and commissioning. Just some main information regarding the photon energy range. So this will go from 10 to 2000. So it covers the soft X-ray, the ultraviolet, and the soft X-ray. I show you here also some the information regarding the optical path, and the flux that we have. That we try to maintain very high, at least in the region 10 to 1,000, 10 to 100. The resolution of the energy also should be very high. larger than 10 to 4 in the whole region, and the spot small enough to see also some small flake or some large flake actually. Then ARPES. So the way we are doing ARPES is using using the analyzer with a movable slit. So this is in our case, it is horizontal, the slit, and we move vertically. And in this way, we get results as this one. So we can get ISO energy images, and then changing the energy, we can get all the band structure of the material that we are measuring. So this is similar to what also Debora was showing before. So we can then reconstruct the 3D image of the band structure of the materials that we can investigate. Some more information. So first of all, the analyzer has a resolution better than 1 millielectron volt when working at 20 electron volt, with angular resolution better than 0.1 degree, and we have 3 modes, or 3 2D modes, from the small angle to the large angle, to cover the below-end zone. Then what we are already organizing is the upgrade with a spin detector. So here we have still this movable slit, and then the electrons go partly on the MCP, and the part are manipulated into a spin detector that is a B-lead. So it has magnetization coils that can change the magnetization direction of the target, and then one can discriminate the spin up and spin down. And then in the manipulator, we can move, actually we can orientate all the spins in all directions to get all the information of the spin information from the sample. Then something regarding the sample preparation. So we have a main chamber, a main distribution chamber, where we have attached many chambers. So the log to introduce the sample, an organic molecule chamber to deposit organic materials, molecules, a UHV suitcase, and the sample storage, and the main preparation chamber. So here we can have all physical preparation methods, something like MBE, sputtering, plasma oxidation, and we have also space for an atomic layer and CVD deposition chamber. This is the main chamber, the analysis chamber. So with the analyzer, and here we have a manipulator, a 6-axis fully motorized manipulator with a very low temperature. So it is better than 10 K. It reached 7 K. And here, this is very important for people who want to work also with devices, not only with the materials. We have the possibility to have 4 electrical contacts on the sample. So one can think to make electrical measurements in the main chamber of the analysis chamber. Yeah? As I said, I wanted to be very fast and to give you more time for questions, because this may help more than pictures. This is just to say that the ARPES is on the way. We are commissioning the beamline right now. And this is a good opportunity for the whole ARPES community, in particular for the Spanish ARPES community. And we will work at low temperature with high resolution in a wide energy range, and we can make 2D measurements. What I didn't mention is the automatization. So we are trying to optimize as much as possible the automatization to make the measurement also for groups with less experience more easy. We have a lot of sample preparation tools. So let me just conclude with the acknowledgement of the whole ALBA people, so all the divisions. Also then to Jordi Prat, Debora, who was here a beamline scientist until December, Federico Bisti, and then to Josep Nicolas, who is the project executive. So I finished, and I would prefer to have questions from you more than showing pictures.
Okay, thank you, Massimo. There are questions already. Felipe Caballero asked about the sample constraints that you can measure. Powders, thin films, can be polycrystalline, amorphous.
Okay, ARPES works mostly with single crystalline. Okay, if we have polycrystalline materials, they should be, let's say, of the order of the spot that we have. So we are not a nano ARPES beamline. So this is different from Antares. So from the images that Deborah was showing before. So we need to have single crystalline. Thin films, for sure. Flakes, if they are large enough for covering with the spot, then this is possible. Or if we have the flakes on some amorphous substrate to remove all the bands that come from the substrate, then this can be also feasible.
Okay, thank you. There's another part of the question that maybe I can help to answer, because he's asking about the possibility to send sample to measure in the actual restricted situation. And well, I don't know if you want to answer respect your.
Yes.
Yeah, this is. I mean, this is possible. In fact, a user that cannot travel to ALBA and they have a beam time, the beam times can be done in remote. This is to send a sample and the staff can measure the samples. And about the possibility of the access to foreign users, I don't know if he's asking on the actual situation, but in principle, there are no restriction to foreign users. About the funding for foreign users, there is the, maybe Manuel can say a word of that, but the European programs, Calypso and this thing are funding European external users, not Spanish.
So ALBA is an open facility, so every person with an affiliation everywhere in the world can proceed and perform experiments in ALBA. And then the point, as mentioned by Miguel Ángel, is the funding. So currently ALBA has no funding for users outside an affiliation that is national, and also in Portugal there is a collaboration with Portugal. So Portuguese users can also be funded for experiments, but then out of, say, charges for the trip of stay, you will not incur in any additional charges. So you need helium for the experiments or things like that. These are everything is provided by ALBA. And then for European users, there are some small possibilities for some modest funding via the Calypso program. In the past, the Calypso program was providing more opportunities, and recently is more oriented also over industry. So the funding for academic uses is smaller. There are other programs that are also interesting, that one of them is called NFFA, and it finished, but there will be a new program starting, I think, this year. And this is also another path for academic users to request bin time through the NFFA European program. I think that you have to apply for different facilities, maybe, I don't know, sample preparation in Trieste, experiments in Trieste, theory in Jülich, experiments in ALBA, microscopy in ICN2, things like that. You have to combine several axes, but then you will be funded for trips and stay.
And he's asking about funding, special funding for Iberoamerica. Manu?
Yeah, sorry. Not that I'm aware for the moment. I know that ALBA management or the director was trying to work out in some opportunities with some European countries. I don't know what is the situation with Mexico, well, but not South America. There were discussions, so maybe in the future there will be something.
Okay, thank you. So there's another question for Massimo from Jorge Lobo.
Yep.
He's asking about the hole in the MCP for the spin detector. How much does it block?
Actually, it doesn't block anything because we maintain the same MCP, okay, and the hole is outside the region of the MCP. So we have a 41 millimeter MCP also when we use the spin detector. Okay.
So let's see if there are more questions or not. Amilcar, want to make a question, please?
Yes, I have a follow-up question regarding the spin detector, and I didn't get the exact technique that you use. It's a mode detector, or it's a different type of?
Is the V lead? Is a V lead? Is a low energy diffraction. So it works at 6 electron volt. It is not like the mode detector that works at high voltage. Okay, it is called V lead, very low electron.
And in terms of
it is better than the mode
diffraction. And in terms of acquisition, because usually the mode detectors is faster.
Yeah, it is faster. Yes, it is about 10 times faster than the mode.
Okay. Okay, thank you.
Yeah. But...
So, if there are no more questions and we are late, I would like to thank to Massimo and to all the speakers in the session and give the word to Manu.
Yeah, well, let me just mention that, well, thank everybody that has been following the session, and we apologize for a small delay, but probably it's understandable. So we'll be back at 3 p.m. continuing this section that Massimo opened, showing with brief talks the capabilities at ALBA, and then with a roundtable where we invite every ALBA user or person that is in the community interested to use ALBA to have a word, propose suggest instrumentations or discuss limitations or ideas for where he or she thinks the field may be moving in the next years. Yeah, thank you.
Thank you.
Bye. See you later.
See you at 3 p.m.